Hello guys, welcome back to Tronics Energy. So last time we started off a short series on how NE555 operates inside when we connect it into different modes. So there are three different modes in which NE555 can be connected. Is an A-stable, monostable, and a bi-stable mode. For an A-stable, the circuit does not have any stable state, so meaning that it will be turning on and off continually without any external triggering. So last time that's what we did, and I demonstrated it, and I tried to explain what really happens inside for the circuit to give that configuration or that setting. So this time round I want us to do a monostable mode. And what a monostable mode is, meaning that the circuit has only one stable state. Once I press this switch, you can see here that circuit will be turning on into a specified period of time, which is decided by the circuit constants. The circuit constants are this capacitor value and this resistor value. Yes. So as we said, the NE555, the external circuitry of the NE555 is what is going to decide which mode you want to set your NE555 to give. Like for in our case right here, you can see the NE555 is demarcated using this dotted line. So if I place my hand here, the external circuitry you can see on my left side is what's that deciding that the NE555 is connected in monostable mode. So for the monostable mode, you can see it contains a switch, a resistor, a capacitor right there, and another resistor. Those are the only external circuitry that you need. Maybe some few jumpers if you are making your circuit using a breadboard. So as we've said, monostable mode has only one stable state, and I'm going to try to explain what happens once the circuit is on. So let's start. So once the circuit is on, once the VCC is on, the trigger pin is set to high because it's connected to VCC via resistor R2. It's going to be high. Then if you can remember, we said that this part of this voltage divider, this is a voltage divider containing these 5 kilo ohm resistors. This part of this voltage divider contains a third of VCC, and this upper part contains 2/3 of VCC. So this is bigger than this. So initially, once the circuit is on, the trigger pin is going to be high, and if you can remember, for a comparator, once the inverting input is bigger than the non-inverting input, we get a 0 output. So since that's our case right here, it means that the circuit is going to give a 0 output. Yes, the 0 output is going to enter this S input of our flip-flop, and our Q bar output will be 1. Like that. Q bar output will be 1. Let's look at this upper part of our circuit. So once Q bar is 1, okay. Then this upper part of the circuit contains the threshold pin connected to that part of before you get to the capacitor and the discharge pin. So because we have said the Q bar output is 1, that 1 enters this discharge transistor, which is connected to the discharge pin at the collector of the NPN transistor. So because this is 1, meaning that this circuit will be on, this part of this circuit will be on, meaning that it's going to discharge this capacitor. It's not going to allow the capacitor to charge. So meaning that it's discharging the capacitor. So if this part is on, meaning that this part is off, this part is going to be low. It's going to be low, 0. So since it's 0, and since the non-inverting input is lower than the inverting input, meaning that this part of the comparator, this upper part comparator, is going to give a 0 output. That 0 is going to enter this R input of our flip-flop, and the output still remains to be on. Okay, since the output is on, once it has entered this inverter, it's going to be turned to be 0 because this is an inverter. It inverts the what you have at its input, so the output is going to be 0. So this is the initial state of the circuit. It should be 0. Okay. Now the next part of the next configuration is when we press this switch. Once we press this switch, It can be a push button. Yeah, this is a push button symbol. So once you press this switch once, then it means that this part of the circuit, once you press, the current is going to come and it's going to go to ground. Going to go to ground in that glimpse, in that pulse. It's going to go to ground. In the same pulse, the current here, the voltage here is going to be low. The voltage here is going to be low since it's been directed, or is going to go to the shortest path possible, because current chooses the shortest path possible to go to ground. So it's going to go to ground, meaning that the trigger pin is going to be low. Once the trigger pin is low, it's going to give a 1 output right here. 1 output, or 1. It's going to give a 1 because it will be lower than a third of VCC. So it's going to give a 1. That 1 is going to enter this S input of this flip-flop. Then the output here will be 0. Output will be 0. Once this is 0, it's going to turn off this discharge transistor, meaning that it is going to allow the capacitor C1 to charge. Okay? And this is going to continue. This is going to continue until the capacitor. Now, okay, if you can see here is 0, so meaning that the output will be 1. So once the capacitor is allowed to charge, it's going to charge and going to this direction of the threshold pin. It's going to charge until it reaches 2/3 of VCC. It's going to charge until it reaches the 2/3 VCC. So meaning that all this time it's going to be on. It's going to be the output is going to be on until it reaches 2/3 of VCC. Once it has reached 2/3 VCC, then the circuit is going to give a 1 output right here. A 1 output. Okay. Once it has given a 1 output, the 1 output is going to enter the R input of this flip-flop. So once it has charged to be 2/3 of VCC, now the output of this comparator is going to give a 1 output, and that 1 is going to enter, and it's going to change the value of the Q bar output from 0 to 1. Once it has given a 1 output right here, then that 1 is going to enter this discharge transistor via the base pin of the discharge transistor, and is going to discharge the capacitor to ground. Once it has discharged the capacitor, the circuit is going to go back into its initial state, where this will be 0 and this would be 0, and the cycle continues. So to do that again, you're going to have to press this trigger switch right here to charge the capacitor. Then once it has charged to be more than 2/3 of VCC, it's going to turn on this point, and it's going to turn on the Q bar. The Q bar is going to discharge the capacitor, and the circuit will go off again. So that's how a monostable operation occurs, and the NE555 internal schematic. So I hope you have really understood that. So I'm going to demonstrate. So this is a connection of an NE555 in a monostable mode, and yes, so let me turn it on. Yes, and it's on. So as we have said, once I press this switch is going to allow the capacitor to charge via this resistor. It's going to allow the capacitor to charge, since this charge pin is going to be off. So VCC is going to come and charge this capacitor, this one right here. Once it has charged to be more than 2/3 of VCC, it's going to turn on this comparator to 1. That 1 is going to change the Q bar output from 0 to 1, meaning that it's going to enable this discharge transistor, meaning that we are going to discharge our capacitor back to its initial state. So that's basically how the monostable operates. So if I press this, it's going to turn on. Then once it has reached more than 2, that's going to be turned off via the discharge transistor inside the NE555 IC. And as we have said, the time or the period at which this output is going to be on is determined by the circuit's constants, which are this capacitor and this resistor. And actually there's a formula to calculate the period at which the circuit is going to be on. And let's do it. So like for in our case right here, I have a capacitor. This is a 470 microfarad. We have a resistor right here, which is a 5.6 kilo ohm resistor. So the formula for calculating the time is usually 1.1 multiplied by R multiplied by C. So this R is the resistance, this C is the capacitance, and 1.1 is a constant of this formula. So for in our case, we have 1.1 multiplied by the resistance, which is 5.6 times, let's 10 raised to power 3, because it's a kilo ohm. We can put this in a bracket, then we multiply that to the capacitance, which is 470 times 10 raised to power negative 6, since it's a microfarad. Then once you calculate this, you're going to get let me see, you're going to get 200, you're going to get 2895.2 times 10 raised to power negative 3 raised to power negative 3. So once you put this, it's going to be a 2.895 seconds. So our circuit, once I press this switch, the circuit is going to be on for 2.8 seconds. So let's see if that's possible. So the 1, maybe 2, then it's going to be turned off. So this formula works. And you can see, if you want to increase the time, you can increase either the resistance or the capacitance, and the circuit is going to be the time is going to be increased into some seconds right there. So I hope you have really understood how our monostable connection on an NE555 operates. And next time we're going to do a bistable, and we're going to finish our series there. Then from there we can continue with our registers. I think I would have gotten the IC which I needed to make that, or to make the last register which we were supposed to do. So thank you very much guys for watching. Please subscribe to Tronics Energy, and I hope to see you next time. Goodbye.